Hey everyone, it's Suso. Today I wanted to show you something quite strange, to be honest. You see, with summer and quarantine, I found myself with quite a bit of time in my hands, along with a very important question. Can you run Super Mario Bros. In Minecraft? Let's find out! So, I've always seen people doing these crazy things like running Doom on a calculator or something, and I wanted in on the madness. The thing is, I had no clue where to even start. But still, I set a goal for myself.
The idea was to make my own NES emulator that can run games in a playable way, using only what was at my disposal in the normal version of Minecraft. That means no mods. Of course, I soon ran into a big problem.
I didn't know how an NES works.
That's convenient. So I found this website called NESdev, and it has tons of information about the system. Whether it's addressing modes, clock speeds, or even obscure bugs, it's there for anyone to look into. And my favorite part, since it's a wiki, it also serves as a random rabbit hole to get sucked into whenever you don't want to do actual work.
Why am I here again?
Anyways, how do we run this thing? The first option that comes to mind is processing everything in a data pack and displaying the result as a giant screen of blocks, but instead I wanted to try a crazy idea. In Minecraft there are a few visual effects that use full screen image filters. For example, the glowing outline, creeper vision, and most importantly the fabulous graphics setting. The cool thing is that we can edit how these effects work using a resource pack, just as you would edit textures or sounds. Here's the plan. We take every single numerical value we will need to represent an NES and put them into the RGB channels of on-screen pixels. Then we take the resulting image and run it through a very complex filter that executes the operations the console's processor should. By doing this over and over, we should theoretically, potentially, possibly, maybe, emulate an NES. After that, we add another filter that transforms this data into proper game video, and we should be good to go.
The cool thing about this approach is that since we can draw directly to the screen, the final results should end up looking pretty crisp.
About 1300 lines of code later, I had an early prototype for the processor. Let's see if it can run some simple code. Say we want to multiply 5 times 7. Does that work? I guess not. After a very dumb fix though, I was able to run some small tests on it. Still, writing machine code by hand and looking up pixels in GIMP didn't seem like the most efficient way of debugging. Luckily, there's this ROM called NEStest, made by Keptris back in 2004. It tests every single CPU operation and even comes with a log of what your emulator should be doing. I just needed a way to load it in. So I made this super simple Python script that turns NES ROMs into images. This way we can just pop it into the resource pack and hope it works. I also made my emulator output the same information as the reference log to the screen. This way I could use another Python script to turn it into a text file, which made it way easier to compare and find bugs. And after a couple days of intense bug fixing, this happened.
So the CPU was ready. There was just this teeny tiny problem. Currently I was executing one instruction per frame. The NES should be doing about 8500 or so that means my emulator runs at about 0.007 FPS. That's more than 2 minutes per frame, and it wasn't going to cut it.
I tried running the filter recursively in the same frame and that just sucked, so I ended up going for a big loop inside my code that made it so a single pass of the filter executed a whole frame worth of instructions, rather than, a single one. Also, there's this 800 line switch case now. Hope it's fine. Implementing this shouldn't be a problem, but there's a catch. Our code runs in what's called a shader. This means that instead of being executed on the CPU, it does on the GPU. And GPUs aren't designed to deal with our shenanigans. The values for each pixel get computed in parallel, so we can't pass information between them. This is inconvenient, but we can get around the limitation
by running the operations on every pixel. So the idea is to run the emulation about 1400 times at once. That's scary. I'm sure I can make it work though. Like, what's the worst that can happen?
Turning it on and... this is taking a while. As it turns out, there's a maximum number of instructions you can have in a shader. I shot straight past it. Time to rewrite some stuff. For example, let's say we have this piece of code. With these conditionals, it looks clear and easy to read, but it's not very well optimized. This option, on the other hand, looks obscure at best. In the end, it will perform better though. Another few minutes of loading later, and that's more like it.
Now that the CPU is working properly, it's time to start with the graphics. This will be fun.
Let's start by implementing video RAM. Oh, really?
I'm starting to notice a pattern here.
Okay, I patched that up, and the result is... not great? But by the next test we were getting there. Notice how these lines here almost begin to look like the case menu. And the next time I tried, my jaw dropped. At this point I had already put quite a bit of work into the emulator, but so far the only thing I could run were CPU tests. So, seeing that Donkey Kong text load was quite something. What we are looking at here are the IDs for each tile on the title screen.
After a few attempts, I got the textures to work, which resulted in this, and if you wait for the demo to start, that. I can see a few things wrong with this screenshot though, so let's try patching the colors up. After all, this isn't a Virtual Boy emulator.
Nope. That's more like it. And after a quick fix, the game's looking almost normal. We are just missing one small detail. Mario... he's gone. Look, I implemented sprites. We have actual gameplay now. It's still a demo, I haven't plugged a controller in yet, so let's do that. To get input into the shader, I made a data pack that changes the color of this armor stand's helmet, depending on player input. Since colors on screen can range from 0 to 255 on each color channel, I can pass 1 byte, which is the same amount of information you would get from an NES controller. I chose a pretty weird control scheme. You move to use the D-pad, left and right click are select and start, moving your camera is B, and scrolling the scroll wheel is A. The idea is that these controls don't interfere with each other, so I can just remap an actual controller to the keys, which ends up being quite comfortable. Let's try it out. This is the menu of the testing ROM I was using before, with a special hardware inside the cartridge. Picture this. You bought a game and it just came with a stick of RAM. My emulator currently only supported Mapper 0 games, which don't have anything weird. So I tried adding support for one more type of cartridge. After some weirdness, I got Mapper 2 to work. This one is responsible, for example, for Mega Man, Castlevania and Metal Gear. Due to that thing, I had to separate the mappers into 2 different resource packs. Also, since this mapper includes extra memory, I now have to run the emulation about 4000 times at once. Oddly enough, I haven't seen much of an impact performance-wise. If you want to try this out, I'll leave a few downloads in the description. First off, there's a world download that has everything ready to go. Pop it into your saves folder and it should work. I'd recommend using this one if you want to have a quick look. Just remember that you'll need to set your resolution to 640 by 480 and your graphics to fabulous. Otherwise, the second download contains a world, 2 resource packs and some Python scripts. To set it up, you'll first need to get an NES ROM and convert it into an image using rom.py. Then, depending on the game, you go into either of the resource packs and place your image under Assets, Minecraft, Textures, Effect with the name rom.png. Then to use it, put the resource pack on and go into the world. You still need to use 640 by 480 as your resolution and set your graphics to fabulous.
And before we go, I wanted to say a few things. First off, this video was inspired by Setling. In case you haven't seen it yet, he made an Atari 2600 emulator a while back, also in Minecraft. So yeah, I recommend checking that out. Also, while making this video, I found out about this series by Javidex9 on NES emulation, and it was really helpful while putting this together because he does a very good job at explaining how some of this stuff works. So I'll also be linking to that. And in case you have any questions, just leave me a comment below, whether it's on something technical or something I didn't explain. I'll try my best to answer them. And yeah, that's about it. Thanks for sticking till the end of this madness.